Hello everyone, welcome back to my channel Ace to Excel. In today's video, we will talk about two special counter categories, that is ring counter and Johnson counter. To start with, I'll first talk about ring counter. When I say ring counter, as the name suggests, the circuit of this type of counter appears to be a closed loop. Right, the working of this counter is similar to shift registers, except one fact that it has a feedback loop, and secondly it is going to count selective number of stages only. Now we have a circuit diagram where I have 4 D flip-flops, and these D flip-flops are 1, 2, 3, 4. Output of 1 is QA, output of 2 is QB, output of 3 is QC, and output of 4th is QD, and QD is connected as a input to first flip-flop, that is QA's input terminal. Second thing which should be kept in mind is that we have a concept of clear and preset. Preset, whenever is 0, the output of the flip-flop to which preset is 0 is always 1, and wherever clear is 0, output of that flip-flop is always equal to 0. So here we have 3 clear connections in the circuit and 1 preset connection in the circuit. That is, the very first flip-flop is connected to preset. Whenever preset will be 0, output of this flip-flop will be 1, and whenever preset will be high, output of this flip-flop will be low. By default, we are considering that flip-flop number 2, 3 and 4 are connected to clear 0. That means the output of these flip-flops are 0, and preset is connected to 0 for flip-flop 1, and output of this flip-flop will be equal to 1. So if we go by the timing diagram, when the very first clock enters, the very first clock comes, due to preset, output of first flip-flop will be 1, and due to clears, output of rest 3 flip-flops are 0. That means somewhere the output is 1, 0, 0, 0. Now this 0 acts as input to the very first flip-flop. That means D receives 0. Now, if you remember, D flip-flop, also known as data flip-flop, this flip-flop is transparent in nature. If it receives 0, it gives output as 0. If it receives 1, it gives output as 1. In this current time, when clock is at second stage, somewhere D is 0. That means output of first flip-flop will be 0. And the previous one is shifted to flip-flop 2. The 0 is shifted to flip-flop 3, and this 0 is shifted to flip-flop 4. So somewhere flip-flop number 2 now gets D high. So somewhere the output appears like this. Again, in the third timing cycle, again at output of 4th flip-flop is 0. That means at third clock cycle, this one which was in output of second comes to input of third, and the 1 shifts ahead, and this is how the circuit appears, still having output as 0 in the third consecutive pulse too. Now when it goes to the next clock pulse, somewhere again shifting occurs and the data is shifted, and if we look into the circuit, somewhere this is 1, 0, 0, 0 equivalent to binary 8. This is 0, 1, 0, 0 equivalent to binary 4. This is 0, 1, 0 equivalent to binary 2, and this is 0, 0, 1 equivalent to binary 1. And if I'll go by the 5th clock pulse, now you have output of flip-flop 4 as 1. Again D gets high, and somewhere again repetition of the same sequence appears somewhere, showing that ring counter always counts 4 number of states. Now, total number of states when connected with 4 flip-flops is 16. Somewhere the circuit is counting 16 states. But actually only 4 states are counted. So somewhere total unused states are 12. And that is the major drawback of ring counter, that no doubt it is a counter which counts, but it only counts 1, 2, 4, 8 if you have a circuit of 4 flip-flops. Next in the circuit is now the second category of special counters is Johnson counter. Johnson counter, also known as twisted ring counter. Do keep in mind the other name of this counter. It is known as twisted ring counter. So this is also a special counter which has a feedback loop, but the only difference between Johnson counter and ring counter is that in ring counter we use Q as the feedback loop. Q is connected in the feedback, while if we will talk about Johnson counter, we will use Q bar as the feedback. Now we'll quickly draw the diagram. The diagram is similar to the one we have drawn earlier, with the only difference that now the feedback will be connected with the Q bar. So we are again making 4 flip-flops. Connection of last flip-flop, that means QD bar is connected connected to DB, QB will be connected to DC, QC will be connected to DD. Now, because we are talking about flip-flops, clock is mandatory, as every flip-flop changes the state when clock is active. So this is the circuit diagram. Now if I go by the circuit diagram, the circuit shows that the circuit is in feedback, and initially I am writing the timing in the words as A, B, C, D, where A is the first flip-flop, B is the second flip-flop, C is the third flip-flop, and D is the last flip-flop. Now initially when there is no clock, every flip-flop is at 0, 0, 0, 0, 0. When the first clock turns up, because feedback is connected with QD bar, somewhere D is 0, that means QD bar is 1, or 1 comes as input to flip-flop A. Because it is D flip-flop, the output appears like this. When the second clock pulse comes, D is again 0. That means QD bar is again 1, or somewhere the value of the output appears like this. At third clock pulse, D is again 0, QD bar is again 1. That means again input is 1, and somewhere the circuit appears this. At fourth clock pulse, D is again 0. Somewhere the circuit is all ones. At fifth clock pulse, now we have D as 1. That means QD bar now is 0. So first flip-flop gets 0 as input, and the outputs at this current state will be this. At sixth clock pulse, again a 0 appears. Output of every flip-flop will be this. At seventh clock pulse, again a 0 is received. Somewhere output turns here. At eighth clock pulse, we receive all zeros, and now if I talk about ninth clock pulse, somewhere QD is 0, QD bar is equal to 1. That means again I am getting the same value as I got in my first signal. First and ninth are repetitive in nature. Now if we take a quick look on What are the values in form of decimals? At the first, it was decimal 8. At the first value, it was decimal 8. This is decimal 12. This is decimal 14. This is decimal 15. Then it is decimal 7. Then it is decimal 3. We have decimal 1 and we have decimal as 0. So somewhere Johnson counter, it counts total number of states as 8. And the states are 0, 1, 3, 7, 8, 12, 14 and 15. Still, unused states are 2 raised to power 4 minus counted states, that is 16 minus 8, or it is equal to 8. So 8 states are used or counted by the Johnson counter and 8 states are still uncounted. This Johnson counter is also known as twisted ring counter, as if you see the shape, the twist appears in the loop, and that is why the other name of the circuit is twisted